Alrighty, welcome to the third video here. This one is going to be on the exponential equation for recursive routines. So 2 videos ago, you learned about recursive routines, which is just a list of numbers that follow some pattern. And to generate that sequence, you needed to have a starting value and a rule, which we often call the ratio. And so in that list, you could generate the next couple of terms in a sequence without much trouble. But if you were asked to find the 1000th term in the sequence, it would be very tiresome to go through and actually have to calculate all 1000 terms just to find out what the 1000th term was. And so this is a formula or a way to get any term in the sequence right away, just with one step instead of having to find all the terms in between. So the equation that we're going to use is, I call it the exponential equation for recursive routines. I'm not sure if it has an actual name. But it involves the first term, and it involves the ratio, and then it involves the final value, or the n+1 term, and the number of times you multiply. So we just said that to get the next term in the sequence, you multiply by the ratio, and then to get the next term in the sequence, you multiply by the ratio again. So what's going on is you keep multiplying by the ratio over and over and over. And furthermore, we just saw that exponential notation is a shorthand way to write multiplying by the same number over and over and over and over. So if we combine those two ideas together, we can use exponential notation to find any term in a sequence. So let me give you a quick example here. Suppose I have this sequence 3, 6, 12, 24, 48, etc. So what's my starting value? I'm starting at 3. And what's my ratio or rule? My ratio or rule is times 2. So get from here to here, I multiply by 2. So I'll multiply by 2. Okay, so if I said find the 100th term or find the 1000th term, you could type in your calculator times 2 times 2 times 2, but it would be nice if there was a shorter way to do that. So the way that you can think about doing that is, you can ask yourself, how many times do I have to multiply by 2 to get there? And then instead of doing it over and over and over and over, just use an exponent. So if I needed to multiply by 2 like 15 times, then I can write that as 2 to the 15th power, okay? So this is the number I'm multiplying by each time. This is the number of steps I took forward. But then you have to also consider, what number did I start with that I actually multiplied 2 to the 15th this many times? So in this case, I started with 3. So I could put a 3 right here. And so 3 times 2 to the 15th, that would take me 15 terms farther into the sequence. So the 3 is the first term. If I multiply by 2 to the first power, I'll get the second term. Then every time I increase the power by 1, I'm going to get the next term and the next term and the next term and the next term. So this is actually going to be the 16th term. So I start with the first term, and then I'm going to go 15 terms into the future. So 3 times 2 to the 15th is the 16th term. So the pattern that this is following is, you put in the first term, which you call your starting value. So your first term or starting value goes right here. And then you multiply it by whatever the ratio is, raised to the power of how many steps forward you want to take. So if you want to find the 100th term, for example, how many steps forward do you need to take? Well, you actually need to take 99 steps forward because you already have the first term. So probably the trickiest thing to remember here is that, well, I've written it right here. If you plug in a certain number for n, that's the number of steps forward you took, but you're actually going to end up one term farther along. So if you take 50 steps forward, you're actually ending on the 51st term. Because if you start at 1 and you count 50 more, you end up at 51, right? So if you wanted to end up at the 50th term, you should only take 49 steps forward. So it's just critical to remember that the n is the number of steps forward, and so the terms that you're finding are going to be off by 1 compared to the steps forward that you took. So I've just drilled it home with another example here. If you plug in n equals 5 and you find this term a sub 5, this subscript of n right here just allows you to keep track of which term you're on. So a sub 5 is how you would pronounce that. And that just means the output value or final value of the term corresponding to n equals 5, which means 5 steps forward. So that's actually the 6th term in the sequence. And all this comes about because we're starting with the first term as 0. And if you want more details on why we start at 0 instead of starting at 1, I'm happy to explain that in class. Just go ahead and ask me, and I'll go through it in detail. So final note on this before we do some examples is the book uses a formula y equals a times ratio to the x. Now this is the exact same formula as I have here. They've just used different letters. So instead of writing a sub n, they write y. And the reason they do that is they like using x and y because x and y can represent input and output. And so, I mean, that is useful. The reason I like using a sub n is because it allows you to keep track easily of which term you're on. So if I say, what is a sub 10, you know right away that means you've taken 10 steps forward and you're actually finding the 11th term in the sequence. Whereas in the book, if they just say find y, it's not clear, okay, well, how many steps forward am I taking, etc., etc. A sub 0 is easy to remember the first term because you've taken 0 steps forward. Remember the subscript here is the number of steps forward you took. So if the subscript is a 0, that means you have not taken any steps forward. So a sub 0 is your first term or your starting value. Ratio is the same, ratio is the same. And then I use n for the number of steps, they use x for the number of steps. So it doesn't matter to me if you like to think about it this way or like to think about it this way. But you do have to understand this formula and see why it works. And think about why it works in terms of this exponential notation that we just learned before with a base and an exponent. So your base is the ratio, and your exponent is the number of steps forward n. And when you're solving these kind of problems, the last thing I'll say here is you have to make sure that you do the ratio to the nth power first, and then multiply by the starting value second, because you do exponents before you do multiplication when you're following PEMDAS. Okay, so let's do some examples. Let's find, given the rule times 3 and the starting value of 5, let's find the 31st term. Okay, so we could start writing the sequence, right? We could start down at, okay, I'm going to start at 5, times 3 is 15, times 3 is 45, times 3 is 105, and we could just keep going. But to do that, to get the 31st term is going to be really, really time consuming. So we can use a shortcut. The 31st term, right? That means I'm taking 30 steps forward. So that means n equals 30. So you remember, the 31st term is only 30 steps forward because you already have the first term. So I can write a sub 30 equals, what's a sub 0? Well, that's the starting value, which is 5. What's my ratio? My ratio is whatever the rule is, times 3. And 30 is the number of steps forward. So I can just go like that. And then I can do this all in my calculator in one quick step. Now I have to remember to do 3 to the 30th power first, and then multiply it by 5. So if I do 3 raised to the 30th power, and then I times by 5, holy smokes, you actually get a super, super big number. You get 1.029 something, something, something times 10 to the 15th power. Okay, so that number is really, really big. And not that useful to write down. That means it's got like, you move the decimal place over 15 times. So this is like, I don't know, over a trillion, something like that. More than a trillion. So another reason why exponential notation is useful is a lot of times numbers are so big that it's easier to write it actually like this than like this. So even though this is the right answer, it might be better to write it in this form. Okay, let's do something more reasonable. Let's find the 10th term in that same sequence above. So in this case we could have, remember the 10th term means n equals 9, and so we can say a sub 9 equals the starting value 5 times the ratio 3 raised to the 9th power. So a sub 9, which is actually the 10th term in the sequence, so take this calculator again, 3 raised to the 9th power, okay, and then times that by 5, because that's your starting value, and here I get 98,415. So the numbers grow really quickly. That's also something you should notice or recognize when you have exponential equations. Even if you start small like 5 and you have a small rate of growth like 3, if you go to the 9th power, this number is getting really, really big. Okay? The last thing we have to talk about in this equation is the difference between a ratio and a rate of growth. So exponential growth is really, really commonly used when you're talking about money and investments. For example, inflation or interest on a bank account, things like that. And so all of those kind of values, they tell you the amount of money that you're going to gain by a certain investment or something, not the total amount of money that you're going to have. And so what I mean by that is you might invest money with like 6% interest, something like that is an example. So you might try to find a stock or open a bank account and get 6% interest. But what they're telling you is not actually the ratio. What they're telling you is the rate of growth. They're telling you how much more money you're going to gain on top of what you already had. Okay? So we know that if the ratio in this equation is bigger than 1, you're multiplying by a number bigger than 1, your answers or your numbers are going to start getting bigger and bigger and bigger. If the ratio is less than 1, then the numbers are going to get smaller and smaller. So say your ratio is 1/2 or 1/3. When you multiply by a fraction like that, your numerical values will get smaller. So if you have 6% interest, you know you're gaining money. So your numerical value has to get higher and higher. And so the way that we can write the ratio, we can write the ratio as 1 plus your rate of growth. So you need to convert the rate of growth to a decimal, and then add 1 to it. And that will give you your ratio. So 6% interest, if you convert 6% to a decimal, it's 0.06, 0.06. And so your ratio is 1.06. So the 1 represents what you already had, and the 0.06 represents how much you've added or gained on top of that. So each time you gain 6%, if you multiply by 1.06, that will tell you how much you have. So if the rate of growth is positive, that means you're gaining money, and your ratio is going to end up being bigger than 1, and your numbers will increase. If your rate of growth is negative, that means that you're subtracting something from 1. If your rate of growth is like negative 5%, you'll do 1 plus a negative 0.05, and you'll get an answer that's smaller than 1, which means your values will decrease. So what if your bank account loses 10%? Okay, then your ratio is 1 plus a negative 0.10, which is 0.90. And another way you could think about this is, if you lose 10%, how much of your value do you retain? You retain 90%, which as a decimal is 0.9. So what if you're gaining 13%? Okay, then your ratio is 1 plus 13% is 0.13, and so you get 1.13. Okay, what if you're doubling? If you're doubling, then you know your ratio is 2, but let's see how this plays out. If you're doubling, how much do you gain? If you double, that means you gain 100% of what you had, and so your ratio is 1, that's what you already had, plus 100% is another 1 that you gain, and that equals 2. So if you're doubling, that's 100% growth, and your ratio would then be 2. Okay, so these are all different examples of how the ratio and the rate of growth are related. Remember that the formula here is ratio equals 1 plus rate of growth, and you have to remember to convert rate of growth into a decimal value. And so your final ratio should be bigger than 1 if you're gaining money, and less than 1 if you're losing money. Okay, so that's it for this formula on exponential growth. And so you can use this formula here as long as you know the starting value and the ratio. You can find out the ending value for a certain term, or alternatively, if you know the ending value and the starting value, you can find the ratio, or if you know the ending value and the starting value and the ratio, you can find the number of terms. So it doesn't matter where the variable is, you can solve this equation for any of the 4 unknowns.